In this video, I'd like to introduce a graphical model for poles and zeros, one which might help you remember which way round they are and understand the effect that they have on the amplitude response. I'll skim over some of the mathematics. For full details, do have a look at the short introduction documents. We'll start here by noting that the effect of a single pole on the frequency response is a factor of 1 over 1 minus j f over the pole. And if I multiply up by minus p and do a bit of rearranging, I will get this. That tells me that the effect on the amplitude response of the pole is proportional to 1 over the modulus of jf minus p. Now, the modulus of jf minus p is the length of this line, a line that joins a point on the imaginary axis at jf to the pole itself. Similarly, for zeros, the effect of a zero on the frequency response is to introduce a factor of jf minus the zero divided by minus the zero, once I've done a similar bit of algebra on this. And that tells me that the effect on the amplitude response is proportional to the modulus of jf minus z, but the modulus of jf minus z is the length of this line from the zero to the same point jf on the imaginary axis. Now to the graphical model. Supposing first there's just one pole, and I'll put this pole at complex frequency of minus 4 Hz. Now, the effect of this pole, as we've seen, in terms of its effect on the amplitude response, is proportional to the inverse of the distance from the pole to a point jf on the imaginary axis. So supposing I plot a kind of a tent shape, where the value of the tent at any point is inversely proportional to the distance away from the pole, I'd get a kind of a shape like this. If I then just take a slice through that shape and highlight its values along the imaginary axis, I would see this. At the moment, it doesn't look much like the frequency response that we're familiar with for poles, but that's because I'm plotting with a linear frequency axis along here. If I was to exchange this linear frequency axis for a logarithmic frequency axis, then I would see this. It's just the familiar effect of a pole, this time at minus 4 Hz. Zeros we can think of as places where this tent canvas is nailed to the ground. I've plotted on a logarithmic scale here, so if you're actually on the ground at a height of 0, then log of 0 is minus infinity. This would head off down to minus infinity. I haven't drawn that bit. But once again, I've just imagined a canvas whose height is now proportional to the distance away from the 0. Doing a very similar thing, just looking at the values of this surface shape along the imaginary axis, and plotting that on a logarithmic scale of frequency rather than the linear scale here, gives the well-known familiar shape of the contribution of a zero that we've seen before. So if you can imagine this kind of tent canvas shape with poles sticking up where the poles are, and zeros as like tent pegs pinning it to the ground where the zeros are, then the height of that canvas at any point along the imaginary axis would give you the amplitude response of your system as a function of frequency. The analogy extends to when you've got more than one pole or zero. Here I've got a case with two poles, so 2 points sticking up through the canvas, forcing it up at minus 2 and minus 10 Hz in this case. And I've got a 0 here at minus 1 Hz. And this is the shape of this surface canvas that I end up with. And this is the value of it in red along the imaginary axis. And if I plot that on a logarithmic frequency scale, I would get the amplitude response which I might expect from these poles and zeros. So that's a kind of a mental model to have in your head about poles and zeros. This canvas draped over the poles and pinned down to ground at the zeros. And then the height of that canvas along the imaginary axis gives you the amplitude response.